High above our heads is a glittering panorama so vast and mysterious that we have spent all of human history trying to unlock its secrets. Why do the heavens move? And where do we fit among the planets and the stars? Looking for answers to these questions, we embark on a 2,000-year journey of discovery that would reshape our Earth and replace ancient stories with a new way of thinking. We invent incredible devices to map the heavens. And a few risk everything to work out our true place in the universe. This is the story of humankind's obsession with the skies and the ways our ancestors made sense of the universe. This is the story of how we moved from a world ruled by supernatural beings to a cosmos revealed by scientific astronomy. This is the story of seeing other worlds and finding our true place among them. This is the story of our ancient skies. From the beginning of time, we have created stories to explain how the universe came to be and how it works. We have learned to watch the skies and to mark the passage of time.
When the sun sets behind that landmark again, boom, you know you've been waiting 1 year.
And ultimately, look into the future. But as different cultures began to share their observations and ideas, our assumptions about the nature of the cosmos began to unravel. For millennia, people across the world assumed the Earth was flat, confined within a universe of limited size and shape.
It does make sense that many of our ancestors believed that the Earth was flat, and that's because the Earth is so huge. It's really a matter of perspective.
But a flat Earth didn't mean an infinite Earth. Because the sky was a dome, then the limit of the world could be found where Earth and sky met. Anyone brave enough to try and reach that limit had to enter the unknown. In ancient Greek epic, the hero Odysseus had to venture to the very limit of the world to find the land of the dead. The closer he came, the more he encountered terrifying dangers, deadly monsters.
We entered the straits in great fear of mind, knowing that on the one hand was Scylla, and on the other, the whirlpool Charybdis. We could see the water whirling round and round, and it made a deafening sound as it broke against the rocks. The men were at their wits' end for fear. Scylla pounced down upon us and snatched up my 6 best men.
might not be flat after all. We spotted clues in the skies.
In a lunar eclipse, the Earth comes between the moon and the sun. So instead of the moon being illuminated, the Earth's shadow blocks some of this light, and you can see the curvature in this shadow.
We also noticed it much closer to home.
If you've ever been out on the ocean and looked out on the horizon and saw a ship sailing away, the ship doesn't just fall below the horizon all at once. It's actually the hull that sinks below the horizon first, and then the mast.
From at least the 10th century BC, sailors were making incredible voyages over thousands of miles, and they found no limit to their world. The ancient Greek historian Herodotus even told a story about Phoenician sailors who circumnavigated Africa. But there was one part of that account he didn't believe. As their fleet rounded Africa, heading west, something unusual happened. The sun now appeared to their right. While it's clear now the sailors must have crossed the equator, for Herodotus, this made no sense. But this was just the sort of observation that could be used by other ancient Greeks who were starting to think in a whole new way.
In early classical Greek culture, around the 500s, 600s BCE, we begin to see the origin of what we now know as Greek science and philosophy. So what the Greeks begin then to do is to leave out the gods and goddesses and begin to focus on the material.
We don't know if there was ever a eureka moment, but by the 5th century BC, this massive eruption of Greek science and philosophy resulted in a reshaping of our Earth, so dramatic that even today, some find it difficult to accept. Our flat Earth broke free from the skies that contained it, reforming into a perfect geometric sphere. Our ideas about the universe would continue to change. But a round Earth was no longer in doubt. The cosmos remained complex and mysterious. But when it came to the Earth, human ingenuity allowed us to move from questions of shape to those of scale.
The question isn't, is the Earth round? The question really is, how big is it?
A mathematician in Alexandria in Egypt took on the task of finding out. His name was Eratosthenes.
Eratosthenes was the head of the Library at Alexandria and most famous for having calculated the circumference of the Earth.
The library at Alexandria had a remarkable ambition: to collect all the world's knowledge under one roof. When Eratosthenes arrived in Alexandria around 240 BC, the resources available to him were unique in human history. But the solution to the problem he faced was actually rather simple.
So how do you calculate the diameter of the Earth when all you've got are the tools at hand and the ground around you? Eratosthenes heard a story that there is a well in Syene, Egypt. And on a certain day of the year, if you look down into that well, you can see all the way down to the bottom. The sun is shining straight down that shaft. Well, he lived in Alexandria, which was due north of Syene. And he knew that on that same day, a stick stuck in the ground still cast a shadow. And he realized that using simple geometry, he could use this information to calculate the circumference of the Earth. Eratosthenes knew that if he put a stick straight into the ground, at the same time that somebody's looking down a well in Syene, this stick will cast a shadow. So if you measure the angle from the top of the stick to the tip of the shadow, that angle is going to be the same as the angle from the center of the Earth to Alexandria and Syene.
Eratosthenes worked out that this angle was about 7.2 degrees. Using this figure and the distance between Alexandria and Syene, he could calculate the size of the Earth using geometry.
Eratosthenes knew that Syene was 5,000 stadia south of Alexandria, and that's an ancient unit of measurement. When he did the experiment and did the math, he calculated that the circumference of the Earth was a little over 250,000 stadia all the way around.
That's about 29,000 miles. Eratosthenes' figure was just 16% more than the actual circumference of the Earth, which is around 25,000 miles, making his incredible calculation one of the greatest feats of ancient science. For the first time in history, we knew how big the world was, but most of its surface remained a complete mystery. Over the following centuries, conquest, commerce, and the growth of the Roman Empire connected countries as far apart as India and Italy. In Alexandria, a scholar named Claudius Ptolemy set out to map this new world. Unfortunately, he didn't have much to work with.
Map making seems to have been pretty rudimentary in antiquity and relatively local. Lots of regional maps. We have very few maps that survive.
Ptolemy worked out a way to unpeel and project our spherical Earth onto a flat map of the world. His methods and data were so good, they were used for over 1,000 years. Even Christopher Columbus planned his voyages to the Americas based on Ptolemy's work. But mapping the Earth was dwarfed by Ptolemy's crowning achievement. An epic project, using math and geometry to chart our vast and constantly moving heavens. And the starting point of this new map was one of the most fundamental ideas in ancient astronomy. Every year, we send hundreds of satellites into space. They orbit our Earth at up to 17,500 miles per hour. Without them, modern life would grind to a halt. But this space-age technology effectively operates on an ancient idea. Satellites behave as if the planet they orbit is the center of the universe. It's a concept that's not quite as crazy as it sounds.
We do not experience the Earth as moving. We experience the sun as moving around us. It's experientially true. It's the world we live in.
Wherever you stand on Earth, the skies and everything in them appear to move around us. For Ptolemy, this wasn't just a matter of perspective. It was a matter of fact. An Earth-centered universe. The first building block in a model that would shape our understanding of the skies for the next 1,500 years. Ptolemy combined the ideas of earlier astronomers with his own observations to build his model of the cosmos. And it relied on science, not the supernatural, to make it work.
Ptolemy tried to create a complete system to explain everything in the universe, but on largely naturalistic grounds without any need for divinities. No gods, no goddesses, just natural processes.
Building out from the Earth, he believed that the heavens surrounding us were spherical too. It's another ancient idea that we still use.
I am standing in one of my favorite kinds of places on Earth. a planetarium. And this is a model of how the sky works. We know that the sky is infinitely deep, but it appears to be as if it were a sphere surrounding us. We are in the inside looking out on the surface of one. And that's what this dome represents. The dome is the celestial sphere.
The celestial sphere wasn't just a pretty metaphor. Something had to be holding the stars in their place. Ptolemy believed that the sphere was real, made out of a mysterious crystalline substance that couldn't be found on Earth. But not everything on the sphere moved in the same way.
So if you were to go out at the same time every night, the stars would appear to be fixed and the planets would appear to be moving. And this is because the stars are so far away that they appear to be fixed points of light. The planets, on the other hand, are so much closer that we can see their motion and we can see how they change with respect to us from night to night.
Ptolemy's model wouldn't work with just one sphere. Each celestial body would need a sphere of its own. First came the moon, followed by Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Beyond that, at the furthest reaches of space, were the stars. Ptolemy combined centuries of astronomy and math to show that movement in the skies was perfect, locking the sun, moon, and planets into circular orbits around the Earth, and finding a place for every object we could see. Ptolemy's model was good enough to explain even the most unusual movements in the skies.
If you just had circular motion and the objects are embedded in these spheres, then everything should be moving very neatly and nicely and in a tidy fashion. But it turns out that's not the way the universe really works. If you go out and observe Mars night after night after night and measure its motion relative to the stars, on occasion it does something really peculiar. It slows down, it stops, it moves backwards, goes in a loop, and then starts moving forward again.
Modern astronomers call this retrograde motion. To accommodate these strange movements, Ptolemy added another element to his model: the epicycle.
An epicycle literally means a circle upon a circle. So if you have an object, say Mars, orbiting the Earth in a perfect circle, Mars is also making a smaller circle around that bigger circle, and that actually can help correct some of the motion that we see in the sky that doesn't fit with it moving in just a single circle around the Earth.
Epicycles meant Ptolemy could explain retrograde motion. And alongside them, he introduced two other workarounds. Firstly, he argued that while everything moved around the Earth, it wasn't quite the mathematical center of the universe. Secondly, he added an imaginary point in space, near to the Earth, from where you could watch everything move in perfect circles. This was called the equant. Combined, they made his theories work in practice. To our modern eyes, Ptolemy's model looks extremely complicated.
It's kind of easy to look back now at this Ptolemaic model with the Earth at the center of the universe, everything embedded in these crystalline spheres and these epicycles upon epicycles upon epicycles, and think it's kind of ridiculous. The thing is, it worked, and you can show mathematically that if you add enough epicycles, you can actually predict the motions of all the objects in the sky pretty well, especially if you're just measuring it with your eye.
Ptolemy's model worked so well, astronomers would cling to it for the next 1,500 years. But his cosmos didn't just live on paper. His ideas were turned into physical models to teach astronomy and to study the skies. At the Science Museum in London, physicist Dr. Harry Cliff has one example.
This is an armillary sphere, and it's essentially a physical representation of the universe according to a Ptolemaic model. So in the middle of the armillary sphere, you've got this small brass sphere which represents the Earth, and then the next closest ring to that is the Moon. Beyond that, you have the Sun, and then beyond that, you have a band of fixed stars. So this only really shows the Earth, the Moon, the Sun, and the stars. The planets aren't included in this particular model.
This armillary sphere is 500 years old, but the history of these objects goes back much further.
There's evidence of armillary spheres going back to ancient Greece and ancient China, so around 2,000 years ago. So they're very ancient instruments. They've been around for a very long time. Armillary spheres were used for two different things. So one was to teach the principles of astronomy, but there are also larger armillary spheres that could be used for astronomical calculations. So for example, calculating the lengths of the day, the times of sunrise and sunset.
Ptolemy's scientific model replaced the gods who once controlled the skies with cold, hard math. But, like most people across the Roman Empire, Ptolemy believed in astrology. The idea that the motions of planets and stars had a real impact on our lives on Earth.
If people and stars and planets all exist as a single system, as you watch the stars and planets move mathematically, you can watch human life move. And if you can project astronomical movements into the future, the logic runs so you can predict what's going to happen to people in the future.
What we see as superstition, Ptolemy viewed as science. He even dedicated an entire book to the theory and practice of astrology.
He's saying the only reason why we need to be able to calculate the positions of stars and planets is so we know what their effects are on our lives.
Practical astrology required the ability to predict the movements of the stars and planets. But to make these forecasts, astrologers needed reliable data. And Ptolemy's work provided the new gold standard.
One of his great innovations was to really kind of lay out in detail his model, put it on a mathematical basis. His astronomy book contained these handy tables which allowed you to predict the motions of the planets, which was useful if you were an astronomer or if you were an astrologer, say in medieval Europe, where kings would make decisions about what they should do in terms of policy or going to war based on the positions of the stars and the planets.
For the next 1,500 years, decisions of life and death, even the fate of kingdoms and dynasties, lay in the hands of astrologers, who relied on Ptolemy's model. Ptolemy was a citizen of the vast Roman Empire, which engulfed the Mediterranean and stretched from northern Britain all the way to Iraq. But 300 years after Ptolemy died, and following centuries of superpower status, Rome was on the brink of collapse.
The Roman Empire ceases to have the sort of command of the world that it did. Certainly by the 4th, 5th century, the world is no longer centered on Rome in the way that it was.
The fall of Rome plunged Western Europe into chaos. Government fell apart. Economies crashed. Literacy retreated. The Dark Ages had arrived. But even as the lights went out in Europe, other civilizations still carried the torch of progress.
I think that the story about the Dark Ages as being a period in which not much is happening is really wrong on a lot of levels. And one of the reasons that we've come up with this idea is because we've looked only at Europe. And I think that if we look in a broader global perspective, what we'll see again and again is that ideas are traveling across cultures.
astronomy was already well established in places like China and India. Now, they were joined by a new culture, also eager to study the skies: Islam.
The Islamic world is an incredible flourishing of cultural and intellectual and scientific activity that we can't describe in any means as a dark ages.
For hundreds of years, the East preserved classical knowledge that would otherwise have been lost forever.
Until about the 12th century, the vast majority of Ptolemy, the works of Aristotle, the mathematical sciences of Greek antiquity were no longer accessible in Western Europe.
Western Europe's loss was Islam's gain.
This inaugurates what we know as the Golden Age of Islam, which runs for several hundred years. There's a fantastically vigorous scholarly culture in which all and any ideas about the nature of the cosmos are discussed.
New observatories sprung up across the Islamic world. Using Ptolemy's system as their foundation, Eastern scientists mapped the skies with unparalleled sophistication, using a toolkit of specialized equipment. At Harvard University, David Unger looks after one example.
An astrolabe is a combination between a calculator and a measuring device. So it allows you to calculate the position of the fixed stars, sun, other astronomical objects at any time on any date.
The earliest surviving examples come from the Islamic world. This astrolabe was made in Persia around 1590.
So an astrolabe is a two-sided device. On the backside is a measuring instrument. This would allow you to sight a star and get an angle of how far that star is, or the sun, up from the horizon. And then you could use that angle either to calculate distances or to set up the other side of the astrolabe properly. So the front of the astrolabe is really where the main action happens. It's a couple of layers. On this base layer, there is a projection of the sky and a grid drawn on the sky projected down to this flat surface. And then above that is a layer that turns with these markers. Each marker indicates a different star, and then this ring represents the movement of the sun. And so over the course of the day, this upper ring rotates around, showing you how the fixed stars appear to move across the sky.
Using instruments like the astrolabe, Islamic astronomers added their own observations to the data accumulated over centuries of research. Some worked to polish Ptolemy's model, adding new calculations to keep it running. But others had more radical ambitions, and they searched for new ways to strip away Ptolemy's workarounds.
The Ptolemaic model is the received model that has worked really well for a long time, and yet it's messy, these equants, these epicycles. It's really hard to work with. So people start to simplify the calculations to reduce the number of epicycles.
They wanted to get back to the fundamentals of ancient astronomy and the idea that objects in the sky moved in perfect circles. From the 11th century onwards, through trade and warfare, Islamic translations of the ancient texts began to return west. But they were entering into a landscape that had been transformed by the dominant force in Europe: Christianity. When it came to astronomy, although they'd lost Ptolemy's science, his model still endured. Because over time, Christians had found ways to fit this model into their own beliefs.
In the Christian cosmos, the crucial factor is that everything is created and ruled over by God.
Particularly in the maps from the Middle Ages, these world maps, we see them imagining God outside the sphere of the fixed stars. And so In that sense, conceptually, God encompasses the cosmos.
Because heaven has to be somewhere, then people conventionally located heaven beyond the realm of the stars.
And if God needed a physical place in the universe, then Satan needed one too. Ptolemy's model had the perfect solution.
Hell would have been somewhere in the center of the earth.
To explain Satan's place in the cosmos, the church turned to scripture.
There was war in heaven. Michael and his angels fought against the dragon. The dragon fought and his angels, and prevailed not. Neither was their place found any more in heaven. And the great dragon was cast out. That old serpent called the devil and Satan, which deceiveth the whole world. He was cast out into the earth, and his angels were cast out with him.
Now, with God and the devil firmly in their place, the return of Ptolemy's written work helped to cement the Christian vision of the cosmos and reveal the mathematical perfection of God's universe. This rediscovered knowledge soon embedded itself in beautiful objects and incredible machines, like the world's oldest working astronomical clock, the Orloj in Prague. Whatever the weather, crowds gather to watch its hourly performance. But this is more than just a clock. If you know where to look, it's a guide to the cosmos that uses an astrolabe showing the horizon of Prague and the position of the sun and moon as they move through the zodiac. Watchmaker Dr. Günther Erstmann has spent 30 years studying astronomical clocks. He's going behind the scenes of the Orloj.
I've never seen it before. The astronomical clock in Prague was built around 1410. Only very, very few original parts are still remaining. The oldest part is the stone-carved rim of the astrolabe outside.
From its earliest days, there's always been more to the Orloj than astronomy.
The importance of an astronomical clock was not so much its elaborate indications or its intricate construction. It was a matter of prestige. It was top-notch technology or pride of scientific achievement and craftsmanship, which had, of course, an astronomical content, but there were only very, very few people who actually could understand the meaning of an astronomical dial.
Something like the clock in Prague is a demonstration of the prowess of the ruler who lives there, that this is cutting-edge science.
The money and know-how poured into the Orloj was evidence of a trend sweeping across Europe. Starting in the 14th century, Western Europe embarked on a golden age of learning, fueled by the rediscovery of classic art, literature, and science. The Renaissance. But alongside a respect for the past, the Renaissance fostered radical new thinking, where revolutionary ideas could come from unlikely places, like the desk of a church official named Nicholas Copernicus.
Copernicus travels to Italy because he's traveling in part to the heart of Renaissance Europe. And he's learning the cutting-edge approaches to texts and approaches to science that go with that.
Copernicus was raised on Ptolemy's model of the cosmos, but he had also encountered the work of Islamic astronomers. And his studies convinced him there was a simpler way to explain the skies.
He is exactly replicating the work of Islamic mathematicians and attacking the monstrosity of the Ptolemaic system.
Copernicus took what he learned in Italy back home to Poland, where he set up his own observatory. As his work progressed, he became more and more convinced that Ptolemy's cosmos wasn't just too complicated, it was fundamentally flawed. And rather than repair this creaking model, he would replace it entirely with a revolutionary new theory.
He's got great views of the stars where he is, and he's measuring precisely their locations in the sky and recording them and performing calculations. And this becomes sort of the data for him that helps him to justify his model of the cosmos.
In 1543, just months before his death, Copernicus went to press. His radical new idea dared readers to question centuries of established thought. The Earth lost its place at the center of the cosmos. Finally, joining the other planets as they orbited around the glowing heart of Copernicus's model, the Sun. Decades of hard work, Copernicus had changed the universe. But no one seemed to notice.
Copernicanism is not inflammatory at the beginning. Some people have even gone so far as to say that Copernicus's De Revolutionibus in the 16th century was the book that no one read. It doesn't cause a stir.
Copernicus's new model didn't change what we saw in the skies. Complicated math and naked eye observations could only take our understanding so far. Breaking this deadlock required a revolutionary new invention. One that would change astronomy forever. The telescope.
The telescope is this moment where scientific investigation changes, and it's not just about the observer. Now it's about the instrument as well. And this is actually a pretty monumental shift. This is the first scientific instrument that extends the human senses.
Telescopes have transformed our knowledge of the universe, revealing the distant secrets of space to anyone who cares to look. But the invention that rewrote our understanding of the skies started off with more humble ambitions.
In 1608, Hans Lippershey invents the Dutch spyglass. He's able to magnify things, and he's presenting this to be sold and patented in the Dutch Republic.
The spyglass was good for spotting ships or surveying landscapes, but not much else. When word of this creation reached Venice in Italy, a genius showman scientist spotted an opportunity. His name was Galileo Galilei.
In Venice, Galileo hears about the Dutch spyglass, and he decides that he's going to improve it, and he's going to get famous for doing it.
Galileo realized that this primitive telescope could transform the way we looked at the skies.
The objects that we can see in the sky are limited by the size of our eye and the size of the lens in our eye. Telescopes are a means of creating a bigger lens, allowing us to catch more light or more photons from space to observe these objects.
The kind of telescope Galileo used was called a refracting telescope. Refraction just means bending. You use lenses to bend light. There are a couple of different kinds. There's the convex kind, which bulges out, and the concave kind, which bulges in. With a convex lens, the light is coming in from one side, and it's focused down to a point. And the problem with that is you can't focus it. You need those light rays to be parallel when they enter your eye. Well, that's where the concave lens comes in, because this is a diverging lens. Light coming in from here spreads out. So if you get these two things at just the right distance, this one will converge the light, this one will diverge it, they balance out, and the light that leaves the eyepiece is then parallel and goes into your eye, and you wind up getting a nice, focused, magnified image.
Hungry for fame and riches, Galileo set about making the world's finest lenses for his game-changing telescope.
The quality of the image you're getting depends on a lot of things. You have to have the lens ground at just the right figure. You've got to have high-quality glass. This is hard to do. Not only was Galileo worried about the optical design of his telescope, he had to worry about how the lenses were made. He did this himself. He actually improved the process, making sure that whatever he had was the best that anybody had anywhere.
Within a year, Galileo built a telescope that packed an unprecedented 20 times magnification. Pointed towards the skies, we could now see further than any human had before, and instantly reveal new truths about our universe.
In 1609, Galileo turns his telescope to the skies, and he begins to look at many things. He looks at the surface of the moon. The surface of the moon, Galileo sees through his telescope, is not a perfect crystalline sphere. It has mountains. It is rough. Galileo sees the matter of the moon to be similar to the Earth. And perhaps if the matter on the Earth and the moon are the same, motion works similarly in the heavens as it does on the Earth.
Galileo's telescope also revealed to him entirely new objects in the skies.
With his telescope, Galileo was able to observe for the first time that Jupiter had moons orbiting around it, something that couldn't be seen with the naked eye. This marked a major advance in astronomy because for the first time, scientists saw that the Earth wasn't the only object with moons orbiting around it.
One of Galileo's great proofs, what he sees as the ultimate proof of the Copernican cosmos, is when he turns his telescope to look at Venus. He sees that Venus is undergoing phases like the moon. So Venus isn't just solid all the time, Venus waxes and wanes. And for him, this shows that Venus is inside the orbit of the Earth and is also orbiting around the sun. That it's not just that the Earth is orbiting around the sun, but that the other planets are as well.
Armed with his telescope, Galileo had made more discoveries than generations of astronomers combined. And he was now certain that he held proof that the Church's official model of the cosmos was wrong. From 1610 onwards, word of Galileo's discoveries spread, setting him on a collision course with one of the most powerful institutions in history.
The Roman Catholic Church had attached itself very strongly to the Ptolemaic model of the universe and also to whatever cosmology it could extract from the Christian Bible.
The problem is, the Bible isn't clear about the structure of our cosmos. Instead, the Church had simply interpreted a handful of enigmatic verses to support its Earth-centered model.
Certain passages in Joshua talk about the sun standing still, and that means that the sun must normally be moving, except when God intervened to stop it.
As far as the Church was concerned, this supported their position that everything, including the sun, moved around the Earth. By questioning this model, Galileo was also questioning the authority of the Church. And the importance of God's creation in the cosmos.
Humanity loses its position of centrality. So philosophically and potentially theologically, this is quite radical.
This was a risky time to hold unusual views. The Catholic Church was struggling to contain the explosive growth of rival Protestantism. In this paranoid atmosphere, those foolish enough to question the established order could expect little mercy. In 1600, astronomer Giordano Bruno was burnt at the stake for his unorthodox ideas. But Galileo wasn't one to keep his mouth shut.
This is a really important thing to understand about Galileo, about his personality, which is that he's a deeply ambitious person. It's not enough to do something, he wants to be recognized for doing it.
So, to promote himself as one of the world's greatest scientists, Galileo wrote piles of correspondence publicizing his telescope and the implications of what he'd seen. But by putting pen to paper, Galileo was playing a dangerous game. One incriminating letter was recently rediscovered in the archives of the Royal Society in London. It's the job of Keith Moore to safeguard this historic artifact.
This is a letter sent by Galileo. This is where he begins to talk about his ideas of heliocentrism and the way that scriptures are used to justify arguments in cosmology. It isn't particularly the scientific view, but it's the idea that the Bible is, in the interpretation of the Bible by the Roman Catholic Church, it may be wrong.
It was one thing to debate scientific theories, but in this letter, Galileo was questioning the Church's reading of the Bible.
So particularly he says things like, you cannot go to the Bible and cherry pick small passages from it in order to talk about science. Science was a thing in itself.
A copy of the letter was picked up by the Roman Inquisition. A tribunal set up to root out dangerous ideas and eliminate threats to the Church by any means necessary. Galileo is now in their sights. He promised their evidence was forged by his rivals and sent the Inquisition a toned-down version. It was never known if Galileo was lying, until now.
So the significance of this letter is that it places the responsibility for the arguments that were circulating in 1613 to 1615 in Galileo's hand.
The crossings out and corrections clearly reveal Galileo's hasty rewrite.
This letter is important because this seems to be the evidence, the smoking gun, if you like, that Galileo did indeed take back the letter to make it more acceptable to the Catholic Church.
On this occasion, Galileo got away with a slap on the wrist. But the Church had woken up to the challenge posed by new scientific ideas. Galileo was forbidden from teaching the theory of a sun-centered cosmos, and the writings of Copernicus were banned altogether. For over a decade, Galileo kept his ideas on ice.
Then Galileo catches what he sees to be a lucky break. One of his friends and patrons, Maffeo Barberini, is elevated to the office of Pope Urban VIII. Galileo has a friend in the highest office in the land, and he thinks he therefore has a certain amount of leeway. He starts writing his dialogue concerning the two chief world systems, Ptolemaic and Copernican.
By presenting two models of the cosmos side by side, Galileo hoped to avoid a visit from the Inquisition. But it was a huge miscalculation. He was summoned back to Rome and put on trial. On June 22nd, 1633, Galileo was found guilty of heresy.
The outcome of the trial is that Galileo is placed under house arrest for the rest of his life at his villa in Arcetri. He's told not to write or publish about Copernicanism ever again.
The Catholic Church maintained its ban on sun-centered theories for almost 200 years. But the genie would not go back in the bottle. And this time, Galileo didn't stay quiet.
He spends his time in Arcetri leveraging a network of contacts and disciples across Europe to publish his two new sciences instead, which is the physics behind Copernicanism. The physics that will prove this Copernican philosophy.
The telescope meant that anyone could now look at the skies and see what Galileo had seen. His voice was joined by those of other astronomers, embracing and sharing fresh ideas. Together, their research ushered in a new era of scientific astronomy. They would finally overturn the ideas of old and bring us ever closer to a true understanding of our skies.